Hello, welcome to the 10th live session of Points of Topology NPTEL University course. This is Shovik and what can concerning mathematics. This is the 10th live session of the Points of Topology NPTEL course, and the course instructor is Professor Sastri. Okay, so before going further, can Mustaq, the one student joins. So Mustaq, can you please confirm whether I am audible and this is the screen visible to you? Mr. Mustaq, can you please confirm whether I am audible and is the screen visible to you? Mustaq, can you please confirm whether I am audible and is the screen visible to you? Please let me know. I hope it is working fine. Okay, before going further, please let me know, do you have any question or doubt from the previous session or anything for assignment? Please let me know. Please let me know, do you have any doubt or any question from previous session or any other thing from assignment or any conceptual doubt? Okay, it seems everything is fine. So now let me Okay, it seems everything is fine. So now let me start some new thing called okay. So let me start new thing called limit point compactness. Okay. So let me write down. It is known as the limit point compactness. Okay. So in the last session in metric space, we have seen that. Hold on. So in the last session in metric space, we have seen that in case of metric spaces, any infinite set has a limit point. Any sequence has a subsequence. So these are equivalent things. But in topology, this is not the case. Okay. So that means if a topological is metrizable, then things are same. But if a topological is not metrizable, these are different situations in that case. Okay. So now let me give the definitions of one by one. Okay. So limit point compact means what? By definition, let X tau be a topological space. Then it is said to be limit point compact if it is said to be limit point compact if every open set has say if every open set it's said to be limit point compact if every open set not open set sorry every infinite set has a limit point. if every infinite set has a limit point. Okay, that's what I mean the limit point compactness. Now the first fact is that compactness implies limit point compactness. So Mustaq, please think and let me know. So here we have to do some. We have to assume that space is compact. We need to show this limit point compact. Okay, that's what we need to prove. Well, it's not difficult. Just you have to think a bit. That's all. Okay. So uh, compactness of limit point compacts. Please think deeply and let me know. Okay. Please take your time. So that means what? We need to start with a infinite set and we need to show that this infinite set has a limit point. That's what we need to do. Okay. So for this, I mean, this can be solved using definition. So please think about it. Let me know and take your time. Okay. Please, Mr. Please try. Please try. Mustaq, please try at least. Any idea, Mustaq, or any guess? I mean, whatever in your mind, you can tell. There is no. I mean, there is no need to hesitate. Okay, so it seems it is difficult for you, so let me go through a proof for this. Okay, so the proof of this is as follows. Okay, let me write to the proof. So hold a moment. Okay, so let X be a compact space given a subset A of X. We wish to prove that if A is infinite, then A has limit point. Basically, this is what we want to prove. Okay, and we prove contrapositive statement. We prove contrapositive statement. That is if A has no limit point, that implies A is finite. Okay, that's what we want to prove. Okay, now the point is that if A has no limit point, that implies what? Vacuously A contains all of its limit point. Okay, I mean, of course, if a I mean A dash empty, then obviously A dash is a subset of A. So there is no confusion. Okay, so by definition, this means by definition. So that means what? By definition, by definition, choose a neighborhood UA of A such that UA intersects A at singleton. Okay, so in that case, the space X has an open cover UA. A belongs to A. Okay. Now my compactness. Now this thing collection areas of an open cover. By compactness. Now by compactness, this collection has a finite subcover. Okay, and that implies this collection finite, that implies that X is nothing but UA1 union of UAN. That implies X finite. Okay, that's what the argument is. Why? Because for each A belongs to a this let's say at a finite number of points. So that is the argument. Okay, Is that clear? Please let me know, Mustaq.
Yes, yes.
Okay, thank you for the confirmation. Okay, so the next definition is as follows. Let X be a topological space. Let X be a topological space. If a sequence xn में sequence in X, then X is said to be sequential compact if every sequence has convergence subsequence. X said to be sequentially compact if every sequence has a convergence subsequence. Okay. Okay. So there is one fact or exercise you can say. If f(x to y) compact, sorry, f(x to y) is continuous map, does it follow that f(x) is limit point compact? So please think and let me know. So here what you need to show, if the continuous map, does its limit point compact, limit point compact or not? Okay. So please think deeply and let me know. Please think deeply and let me know. So what you have to take you have to take infinite set of what affects it and show it always have a limit point or not. Okay. Okay. So how to do that? Okay. So the argument is follows. So so it is true first of all. So there is no question of whether it's true or false. It's true anyway. So let a subset of fx be infinite. Okay. We must show that. Sorry. We must show a has a limit point. So choose all those b, so all those x, such that if of x belongs to, that is, it is what this is f inverse of a. Of course, f inverse of a, this is also infinite. Okay. So that implies what f inverse of a has even call it u. So that implies what a has limit point f of little u. That is the argument. Is that clear? So that means what we have done. We start with a infinite set. Start with a infinite set, and then finally we consider f inverse which is infinite, and finally showed that it has limit. But given the fact that a has a limit point, okay. So that's what the argument is. So please do think deeply and let me know. I shall get back to you in a few minutes. Okay. So I hope that's clear. So now there is a concept called local compactness of one point compactification. Okay, let me write it down. Okay. Okay. So local compactness means what? So let X is said to be locally compact at X if every compact subset C of X has an open neighborhood containing X. This is what we mean by locally compact. Okay. So for example, Rn, it is locally compact. Similarly, any metric space is locally compact. Okay. Now there is something called locally compact house. There is locally compact plus house drop. So there is a criteria. I mean, there is theorem. Let me state the theorem right now. We shall get to the proofs later on. Okay, but right now proof is not important. Let X be a space. Then X is locally compact house drop if and only if there exists Y satisfying the following condition. That means what? Local compact house drop means there is a space Y which is compact house drop such that X is a sub of Y y minus x singleton y is compact Hausdorff. So that means what? If space is locally compact Hausdorff, if and only if there is y satisfy the following conditions, then this thing is said to be locally compact. Then that's over Hausdorff. Okay. So that is the thing. So I mean, so the motivation is like if x is not so it turns out that if x is locally compact Hausdorff, that means it only there is a one point which is compact. For example, mm, we have a circle minus no open end. Okay. Now it's a locally compact Hausdorff. Now it's if we choose one point and join these things, then what we will have full circle S1. So that means what? That means instead of this, if you consider the real line or some interval, and then if we bend this, and then if we join by adding one point, then it will circle. So that's why the one point compactification of R is S1. Similarly, what is R disjoint union R with local compactification? What's that? Simple. This is our R. Now this thing can be pictured as follows. So if you put one point here, everything put together, that is this coming. So this is known as S1 wedge S1. Okay. So R wedge R amplification is S1 wedge. Similarly, R wedge R wedge n times each one point amplification equal to S1 S1. Okay. Now the thing is that okay, now there is a fact exercise show that X compact house draw and A is a closed subspace. Then 1 point compactification of X minus A is the quotient X by A. Well, so here I am assuming that few of the students know basic quotient topology, but that's a fact. Let's not prove into this, okay? Currently, we are not in the position to prove this type of statement, but you can take this thing as an exercise, or you can think later on if you're interested. But right now, this is beyond our scope, okay? So the first exercise, first problem is as follows. First problem is show that Q is not locally compact. Q is not locally compact. So please think, let me know. Take your time. Okay, so Mustafa, are you able to figure out why Q is not locally compact? Any case or any idea? Please let me know. The solution is follows. So the solution will be uh, by method of contradiction. Suppose Q is locally compact. Suppose Q is locally compact. Okay. So X belongs to EB intersection Q sub of K sub of Q. K is a compact. Okay. Now from AB, choose a sequence of rationals in AB such that converges to some R. R belongs to Q complement. So Xn belongs to K sub of Q. So that implies R belongs to K sub of Q. But we by choice R is Q complement. So that is the contradiction. Okay. So what's the contradiction? The contradiction is that if we choose an point, suppose it is compact. So we choose an X belongs to open intersection Q sub of K sub of Q. Now I choose a set of rationals in AB. Now Xn belongs to K sub of Q and R belongs to K sub of Q. So that's the argument. Okay. Is that clear? I hope that's clear. Okay. So that is the argument. Okay, I hope that's clear. Okay. Now the next question is that huh, show that theta positive integers its 1 by multiplication is the set 1 by n belongs to. Okay. We need to show that theta positive integers 1 by multiplication this. So hint is that use compactness of this the set 1 by n belongs to n. Okay. So please think about it. Let me not take your time. So Mustafa, any guess or idea how to approach this problem? That means what? That means how to. Okay, that means what? That means we need to find an continuous map from set plus. So that's set. Satisfying those properties. Okay, that's the only target we need to do. So that means what? We define a map YAF. Define YAF. What where z plus 2x with n going to 1 by n. Now it's a discrete z plus discrete. So that implies f is continuous map. Okay. And it is well known that, hold on a moment please, and it is well known that the set 1 by n union 0, this thing is compact. This thing is compact. It is known. So that's why so that implies what? That implies this z plus 1 multiplication is s. Okay, so that is the argument. I hope that's clear. Now next question is that if f x to y continuous, show that if f is open map and x locally compact, then that implies that f of x locally compact. If f of x to y continuous, if f is open and x is locally compact, we need to show that x is locally compact. Okay, so that's what we need to show. Please think and let me know. I shall back within a few moments. Well, so any idea or any guess how to approach this problem, Mr. Mustafa? So this just it will follow from definition. So it really has nothing to do very complicated. Okay. So Mustafa, any idea, any guess? Okay. So let me write an argument for you. Just hold a moment, please. Hold a moment. Okay. So the solution is as follows. So given f is open map, okay, and what we need to show that f is locally compact, okay. Choose the point fx belongs to fx. Now since x is locally compact, we must have x sub of c sub of u sub of x. Where c is compact, u is open, right? This implies f of x belongs to f of c sub of f of u. Okay. Now if f of u is open as f is, and f of c compact as f continuous. So that means what? We are successfully able to make sure that our f of x lies inside f of u, f of u is open, so f of is compact. So, okay, that's what we need, correct? So what? So that's the target. That's what's the target. That so that implies what? That implies f of x locally compact. Okay, that's the argument. I hope it's clear. Okay, so that's the thing. Now, the next thing is the next thing is that countable and separation axiom. Okay, let me do the countable axiom. Countability axiom. So, what does this tells? Suppose X be a space, then X is said to have countable basis at X if there is a countable collection of, sorry, if there is a countable collection beta of neighborhood of x such that each neighborhood of x contains at least one of elements of B, and a space which has a countable basis at each of its points is said to satisfy the first countable action. Or to be first countable. Okay. So that's what the argument is. Okay. That means what? By first countable means what? There is a collection of countable basis. That's all. Okay. Now the question is that what's the use of this first count? Okay, we'll see the use of that. But before that, there is a notion of second countable reduction. A space X is called second countable if it has a countable basis for its topology. It is called the first topology. Okay. So first try to show that second countable implies first countable. So please use the definitions of countabilities and try to show that second countability implies first countability. Okay, please think about it, take your time, let me know. Okay, so Mr. Remind you, I guess, how to approach this problem, how to show the second countable as first countability. See, the process is simple. So choose x belongs. We need to find a countable basis at x, correct? That's what we need to find. So what we'll do, we collection all those beta prime. This contains all those b such that x belongs to b. So of course, this beta prime is countable. Of course, beta prime is a collection of b. So that implies what? That implies this subcollection beta prime is countable, obviously, and it's a basis around x. Okay, so that's the argument. So that tells that um, second count does first count. Okay. Now, there are advantage of being first countable. Okay. So theorem is that let x be a first countable. Then x belongs to a closure if and only there is a sequence xn in A such that xn converges to A. Sorry for the inconvenience due to some unavoidable technical issue. My screen got frozen. Anyway, okay. Musta, can we confirm whether is the screen visible to you? Musta, can you please confirm whether is the screen visible to you?
Yes, you have to fix actually. Now it is okay.
Okay. Thank you for confirmation.
Yes, it is.
Okay, so where are we? So basically, we need to show that if a space is first countable, then x belongs to a closure if there are sequence in xn in A such that xn converges to. Okay, so that's what we need to show. Now the point is that, so that's what it is important. So let me do the one direction. Suppose xn be a sequence in A such that xn converges to A. We need to show that x belongs to a closure. Okay, that means what? We choose an open set. We choose an open set U containing x. I want to show that U intersection A non-empty. Correct. Now if we choose an open set U containing X, then just hold a moment. Now some internet issue again. Okay, just hold a moment, please. Okay, I'm extremely sorry for the inconvenience. Okay, so that's what we need to show that U belongs to X. Okay, so which is equivalent to showing that now we choose U belongs to X since the sequence Xn converts to X. That means what? After a certain step, the sequence Xn belongs to K, and this Xn is already part of A. That implies what? U intersection A is non-empty. So one direction is obvious. That means what? If that means X belongs to A closure. This part is done. You have to do the rest of the part. That means what? You need to show that if X belongs to A closure, that means what? You need to show that if X belongs to A closure, in that case we'll always get a sequence Xn in A which converges to A. Okay, please think about it, let me know, take your time, please do think. Okay. So the okay. Mustak are able to figure out how this can be solved. Any idea? Any guess? So the technique is as follows. Okay, so the hint is, so let me give you the hint. Okay, so UN be collection of countable basis x. Okay, choose x1 belongs to u1, x2 belongs to u1 intersection u2, x3 belongs to u1 intersection u3, dot dot dot. So we find out a sequence x. We need to show that the sequence xn converges to x. Please think about it, take your time, let me know. Please try to do by yourself. We need to show xn converges to x. That's what I need to show, okay? So please think, take your time. So any idea and guess how to show that mm, this xn goes to x? Any? So see. So for that, we need to start on the open set x belongs to x. Okay, that means x belongs to un sub of u. Again, the whiteboard is not working. God knows what happens with this whiteboard. Okay. Now xn belongs to x. Okay. That implies what? No sooner we have xn belongs to x. So that means what? So we choose an open set u containing x. Okay. That means by definition x belongs to un sub of u. So that means what? Xk belongs to un for all k greater than or equal to n. That means what? The sequence xn converges to x. Okay. That's what. That means what? So that was x means a closure implies there exists a sequence xn in a such that xn converges to x. Okay. That's what we proved. Now, now the next fact which we are going to prove is that f is a continuous function x to y. Okay, f is a function which we wish to show that f continuous if and only if f of a closure subset of f of a hollow closure for all a. I mean, we know that in matrices this is the criteria for being continuous, but in topology usually that's not true. We will share some examples, but in generally for apart from the first countability, this type of situation are occur that tells the if continuous implies if of a plus if of whole closure. That's what I need to show. Okay, so please think about it, take your time, let me know. Okay, so it shouldn't be very difficult. Please think about it and let me know. Please take your time. Any idea, any guess how to solve this problem? Okay, so the solution is as follows. See, the point is very simple, okay? Uh, one direction obvious, there is nothing to do. We are going to another. We basically suppose f of now that means what? Now suppose choose x in a sequence in x such that f of xn goes to f of x. We shall show that f of a closure subset of f of a whole closure. Okay. Okay, so what to do? That means that's what we need to show, correct? So what we'll do? We'll choose y belongs to f of a closure. Okay. That means y is equal to f of x belongs to a closure. Okay. Now x belongs to a closure means there is a sequence xn in a, xn goes to. So by the given hypothesis fxn goes to f of x, that is equal to y, and this f of xn lies inside f of a. That means what? Y belongs to f of a. That is, we have proved that f of a closure sub of f of a whole closure. So that's what we proved. Okay. So that's what the argument is. I hope it's clear, Mustaq. Now there are a few properties in the line. The first property is that the first property is that if a space X is uncountable, then every open cover is countable subcover. It is known as Lindelof. Second is there exists a countable dense set of X. It is known as separable. Okay. So the proof is latter. We issue the proof latter. So that means what? If a space is second countable, then it has a countable subcover, which is known as Lindelof. And second is that every open there is a countable dense subset of X. Okay, that's the thing. So that is the property. So the next thing is that we will see the proof later on. Right now we are not interested in the proofs. It's just waste of time. So the proof shall be done later on. Okay. The next fact is that whether R is lower limit topology is not second countable. So R with lower limit topology not second countable, but is first countable. Please think and let me know. So we need to show that R low limit is a set countable first countable. Okay. Of course, it's first countable. That's obvious because if we take x, I mean, if we take any x belongs to R, cos x belongs to x comma x plus 1 by r. So there is nothing complicated. And why not first countable? That's because if it is second countable, then x belongs to bx sub of x comma x plus 1 by n. Okay, and that tells that infim of bx equal to x. That means the collection of bases beta x is actually infinite, actually uncountable. That tells that R with lower limit topology is second countable, is not second countable. So that's the argument. So what does this tell? This tells that it is, so that tells that, so this implies that it is not metrizable. So that's what the argument is. Okay. So that's the thing. So that's all for today. Um, in next session we shall solve some more problems. Okay, so that's the thing. So if you have any doubt or anything, please let me know. Mustaq, in case if you have any doubt, please let me know. Or else we may leave the session if you don't have any doubt. Okay. So okay, that's all for today. We shall meet on uh, next. We shall meet on next Sunday. Thank you. I am leaving the session.